Okay, so today I'm going to give a presentation about lattice-based cryptography, which is a kind of post-quantum cryptography. That is named because it's quite difficult for even a quantum computer to solve the challenge. Um, so that it ensures the security of this cryptography. So maybe let me give a brief introduction to myself first. My name is Jason, and I'm a year 4 student from the School of Science. I'm totally a math guy, not from engineering or computer science, computer engineering, but no worries. I will share something related to math and share how to make use of this math knowledge in the CTF demonstrations. Okay. So before all of other things, let me repeat the code of ethics. So all the exercise and all the techniques uh, shared are only should be only used in the secured lab environment, and it should not be used illegally. And you should bear legal responsibility for misuse of the techniques. Okay, so let's start. Okay, so let me introduce a math concept. What is a lattice? Okay, lattice is actually an infinite set of points. It contains periodic pattern and is generated by taking all the possible integer combinations of some basis vector. So for example, we have a basis 2, 0 and 1, 2. Then we can form two basis vector. Vector A is 2, 0 and vector B is 1, 2. So this is in the two-dimensional space. So we have this vector A and this vector B. So of course, these 3 points are uh, the points within the lattice. And by some integer combinations, like if we have A here and B here, so we will give this point. So this point is also a point in the lattice. So if you further extend, like extend a B here, so we will also get this point. And for example, we extend this, one more A, we will get this. So repeatedly doing this operation will get the lattice, which is the combination of the black dots. So here's some example like -4, 4. This point is generated from -3a and plus 2b, and this is -2b plus 2a. This is -1b and plus 3a. So this shows how a lattice is formed based on the given basis vector. Okay. So let me have a question for you. So this is the lattice and this is the basis. So what is the shortest non-zero vector in this lattice? Or simply, which point in lattice lambda is closest to the origin? So of course, it should be one of these 2 points. Yeah, it's not origin because this is a 0 vector. So it should be one of these 2 guys. So which one? So we can perform a very simple distance formula. This is 2 and this is square root of 5 by Pythagoras theorem. So of course, vector A is the shortest. So it's very obvious because this basis vector is a good basis or a very reduced basis. So they are the most perpendicular basis within the plane. So you may wonder why is not this as B? Actually, they're the same because if we consider the angle between A and this vector, so it's still this angle. So this angle is still the same. So this is already the most perpendicular and reduced basis within the lattice. Okay. Okay, so let's give another example. For example, we have another basis like this 4, 4 and 3, 2. So we construct two basis vector C, which is 4, 4 and D 3, 2. So we see that these two vectors are longer and less perpendicular or more parallel. So you may think, oh, it may give us some letters a bit different. But actually, if we perform some integer combinations, we see that actually it represents the same letters pattern as the previous example. So this is some example. This is negative C plus 2D. This is C and minus 1D. And this is minus 2D and plus 1C. So you see that actually they form the same lattice pattern, and you can conclude that the basis of a lattice pattern is not unique actually. So let me ask you the same question. What's the shortest non-zero vector in this lattice? So actually the answer should be the same. So after we draw out the complete lattice, we see that this point is the closest to origin. So the shortest vector must be this one. However, it's less obvious. So if I don't draw out this lattice pattern and you only have this pattern, this two basis vector, it may be a bit harder for you to find out the shortest vector problem. Okay, so we may call it a bad basis because they are more parallel and longer. Okay, so let me give you one more example. For example, we have this. Okay, so it's hundreds of numbers. So the two basis vector is basically some 300 something, 200 something. And if I ask you what is the shortest non-zero vector in this lattice, you may think that is really hard to find. So it's an even worse it's an even worse basis vector because they're very parallel to each other and very long. But the fun fact is that they actually generate the same lattice pattern as the previous two examples. So as they have the same lattice pattern, they have also the same shortest non-zero vector, which is also 0, 2. Okay. So how to say which one is a good or bad basis or basis vector, and how to do the conversions, we'll discuss it later. So we see the process of this simpler or good basis. This is a more complex, more random, or more bad basis. So they are long and more parallel. This is shorter, and actually is the shortest and the most perpendicular basis vector. So from this simpler or good basis, it's actually easier for us to generate the bad basis. So from a good to bad, the process would be easy. But if we have a bad basis, we want to convert it into a good basis. So this process would be hard. So you may say that in 2D or 3D dimension, 3D space, it may be equally easy. But if it's in a 1000 dimension, and I give you two vectors that are very close, very parallel, so this process must be hard. Okay. So the hard problem is the shortest vector problem. So we will introduce the shortest vector problem and the closest vector problem. Actually, they are very similar. And the cryptographic ideas behind is that also we have something easier to generate another, but it's difficult to reverse the process. So this is perfect for cryptography. It means that we can use this as the public key and this as the private key. So we have this private key and generate a public key, which is public to all the others to encrypt their message. And then as this public key is used to encrypt the data or the message, and it's very difficult to recover the private key. So it only allows the people owning the private key to decrypt the message. So this is the cryptographic idea between this math problem. So the shortest vector problem is actually find the shortest non-zero vector in the lattice, or find the point in the lattice which is closest to the origin. And the closest vector problem is very similar, but it's a bit different here. So it means that, so if we have a lattice, like we have some lattice pattern like this, like something like this. Yeah, maybe just something like this. And then it's in a very high dimension. And we have, so if we have the private key or the good basis, it's very easy to find out all the points in the lattice. So if it's in a very far away place, we randomly select a point here, and then we shift it a little bit. We shift it to a little bit here. So this green dot is not on the lattice. So if you don't have the good basis, it's very difficult to recover from the green dot to the red dot. So this is the closest vector problem, which is we have a point not in the lattice, but we need to find out the point in the lattice that is closest to that point. Okay, so that this is the closest vector problem, but today we will only talk about the shortest vector problem. Okay, so because it's a little bit simpler. Okay, the shortest vector problem should be hard for a generic lattice. So how to make it harder? Just give a more random basis, more parallel, longer basis, and use it in a higher dimension space. So like in the examples, we maybe use 2-dimension or 3-dimension, but in cryptography, maybe we use a 1000 dimension to do the encryption. Okay, but for in our example, we use some very simple case, which is likely that is like less than 4 dimensions. So it would be simple enough for us to do the analysis. And we use some efficient algorithms to compute a solution or an approximation for the shortest vector problem. Okay, so the algorithm between the reduction is actually, the idea is that we use the good basis to generate a public key, a bad basis, and our exploitation would be the reduction algorithm. So in 2-dimension, it would be Gaussian reduction or Gaussian elimination. So this is the knowledge very close to that taught in the DSD-M2 syllabus. And for higher dimension, we will use an extension of the Gaussian reduction, which is called the LLL algorithm. So this process will give us a reduced basis, which is having an equivalent lattice as the more complex one, but it will give us a nearly shortest and most perpendicular basis vector for us. Okay. Okay, so maybe we can start from some demonstration. Okay. Okay, but I will introduce some concepts, some math concepts behind the demonstration. Okay, so you can go to this GitHub repository, or if you are lazy, you can just type in a simpler link, which is math.icu. Okay, so it will redirect you automatically to this page. Okay, so this is the challenge that we are going to discuss today. Okay. Okay, so actually, we need to prepare our environment, which is the Sage Math. It's actually recommended to compile it on your machine for the best compatibility, but the compilation may take a very long time. For myself, I took around 40 minutes to compile it completely. So maybe it takes time. It takes some time. So if you don't get enough time today, we can just discuss it here first and try it later. Okay, so basically, for example, in Ubuntu 24, we need to install a lot of dependencies and then build from the source. So it's a bit different from other libraries, which is a bit easier to install. So we'll clone the GitHub repository and then do the configuration. And then you can run it in parallel. So for my machine, I have 6 cores of CPU, which can be checked via this command. And then you just twice your number of core of your CPU. Like if I have 6 cores, you times 2 get 12 threads. and then compile it on a 12-thread parallel compilation. Okay, and after the compilation, this would take a very long time, and then you would need to create a symbolic link so that you can just type in sage and then something, and then in the shell, and then you can use the functions in the sage. And then we can use the Python shell within Sage. But before that, we need to install some packages from Python. The command is sage and --pip and then install some packages. And then finally, we can perform sage and -python and then path to the Python program. So instead of just directly running the Python program in our own shell, we'll do it in the Sage cell. Yeah, in the Sage shell. Okay, so now let me introduce the mechanism behind the conversion between a good and bad basis. So we know that a bad basis is a public key, and then a good basis is the private key. So it's very easy to come out a private key just randomly 2 short vectors, and then we use these short vectors to generate some very big numbers and very close vectors, which is called a bad basis. So how to perform this? So what we will use today is called unimodular transformation, which will give us an equivalent lattice. So the requirement is that the transformation matrix have a determinant of positive or -1. So this is called a unimodular transformation. So suppose we have 2 good basis vector A and vector B in a 2-dimensional space. So our target is to obtain a very long and nearly parallel. So like in our example, we have this 2 very short and a bit perpendicular basis as a good one. And then we will need to generate some very long and very close vectors. So this is the bad one. So these are A and B, and these are C and D. Okay, so this is our target to convert it. Okay, so it's actually very simple. We define vector C and vector D be m times vector A and n times vector B, and m and n are very large and co-prime integers. What is co-prime is that their GCD is 1. So a very example is 2 consecutive numbers like 999 and 1000. So the 2 consecutive integers would be co-prime. Okay, so we randomly choose some very big numbers to be m and n. And for vector D, it's actually a very slight movement from C, or a slight perturbation of C. So this can ensure that they are very close, very parallel. So actually, we just make m to be m plus k, and n be n plus l, and k and l are very small integers like 1, 2, 3, or -1, -2, -3. So this process will give us a very random, but what we required for the bad basis. Okay, so mathematically, we have vector A and vector B before, and then we have vector C and vector C after a process. So actually, this is done by a transformation, and the transformation matrix U is this one. So we can just do a proof by expanding this matrix to be this. So we will see that this is vector C, this is vector D. So this is actually what we want. So as mentioned before, for a unimodular transformation, we have to select ML and MN such that it fulfills the determinant requirement that ML minus NK will be equal to positive or -1. You may wonder why it's ML minus NK, because for determinant, it's these two times each other, mn plus ml, and then minus these two, so it would be mn minus k. So after canceling out these two terms, it would be, sorry, n, yeah. So after canceling these two terms, we'll get the, sorry, I cancel out the wrong term. So this would be canceling out mn and minus mn. So it will give us ml minus this kn. Okay. So the determinant must be equal to positive or negative 1 to ensure that the transformation is unimodular. That is, it preserves or maintains the equivalent lattice. Okay. So a very simple example is how does the example in my previous slides are generated. So we have two basis vector, 2, 0, and 1, 2, and we define, so I do a swap here because it would be easier for us to do the examples later. Okay, so we define vector D to be MA plus NB and C to be a very slight movement from D. And then we select M and N to be 199, which are very large, and they're co-prime because they are consecutive integers. And then we would test some small integers, like maybe we substitute K and L be 1, and then we test ML minus NK. Oh, it's 1, so it's perfect for a unimodular transformation. So we just choose these four numbers and then find out the vector C and vector D. So it will be these two vectors. So because this is a unimodular transformation, so they are in the equivalent lattice. But however, it generates a bad basis for us. So it's a bit difficult to convert it back to a good basis, which is this very simple one. Okay. So we just discussed how to generate from a good basis to a bad basis. So here's the problem, how to convert it back in some low dimensional space. So if it's in 2 dimensions, we have Gaussian reduction. So this algorithm can only be used in the two-dimensional lattice. Okay, so if we have a lattice generated by two basis vector v1 and v2, and then we want to find out the shortest basis vector. So we will perform this loop. So this loop is basically the algorithm between Gaussian reduction. So it will first compare the norm of v1 and v2. The norm means the length. This is called a norm, or we can call it the length or size of this vector. So for in the two-dimensional space, we can just perform a Pythagoras theorem to this to find a length for v1 and v2. So if the vector 2 have a shorter length than the vector 1, so we will swap v1 and v2, and then we will compute m. So m is given by this formula. So it's v1 dot v2 to calculate the dot product. So this would be a number. So two vectors dot product would be a number. And then, so this is actually the square of the norm of v1. So this is also a number. So two numbers divided by each other. And then if, and then a very important thing here is this symbol. So this symbol means rounding off to the nearest integer. So if we have 0.49 something, so it will give us 0. And if we have 0.5, it will give us 1. And negative 0.49 give us 0. And negative 0.5 also give us 0. But if it's negative 0.51, it will give us negative 1. So this is basically the idea. So it ensures that m ensure M is between negative 0.5 and 0.5. So we will explain why in the next slide. So if M is approximately equal to 0 after rounding off, so we will replace V2 by V2 minus M times V1. So we'll continue the loop, and then finally we will get V1 and V2. They are the shortest basis vector for this lattice, and the front one, the V1 would be the shortest non-zero vector in this lattice. So it solves the shortest vector problem. Okay. Okay. And let's see. So this is the math related to this algorithm. We have some notes. This is the norm. We've just performed a Pythagoras theorem in 2 dimensions. If it's in a higher dimension, we just take the dot product of the vector itself. So maybe for a V1, V2, the vector is the vector for vector V equals V1, V2, dot 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 Vn. So perform the norm of this vector would be V1 square plus V2 square plus dot 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 plus Vn square, and square root the whole thing. So this is called the norm, or the size or length of this vector. And note 2 is that the angle between 2 vectors. So if we have V1 and V2, so there's an angle between 2 vectors. So by the math formula, cosine theta, so cosine of this angle is given by the dot product of 2 vectors, and then divided by the norm of the 2 vectors multiplied by each other. So if we take the absolute value of the 2 sides, we will have cosine theta equals this one. And in our algorithm, in the Gaussian reduction algorithm, we have M equals to the dot product of V1 and V2 divided by the square of the norm of V1. So it's actually this one. So as I said, the rounding off function ensures that M is between negative 0.5 and 0.5. So if we take the absolute values, it must be less than 1/2, which is 0.5. So if we divide both sides by the norm of V2, and also multiply the both sides by V1, okay, so just multiply both sides by V1, the norm of V1. And then we will see that this one will be less than 1/2 times the norm, the ratio of the norm of V1 and V2. So actually this one is absolute value of cosine theta, which is the absolute value of the cosine ratio of the angle between 2 vectors. So because in the algorithm, it ensures that V1 is less than V2. So if they are not in this relationship, we will swap. So it ensures that in this process, V1 is shorter than V2, and they're both positive because their vector, the length must be positive. And it ensures that this ratio must be less than or equal to 1. So that the above must be less or equal to the below one. So this thing is actually less than or equal to 1/2. So if we have this ratio, absolute value of cosine theta is less than 1/2. So if we plot the cosine graph out, so what's the cosine graph within so for the right side, it would be something like this. Okay, so this is this is 180 degree. Okay, So this is the cosine graph. So if we have cosine theta to be within these two values, so we must have the angle to be within this. So actually, this is 60° and this is 120°. So we ensure that the two vectors should have an angle between 60° and 112°. So this ensures that the two vectors are actually very perpendicular to each other, and it implies that we cannot make the vector v2 smaller by subtracting the integral multiple of v1 from v2. Okay, so this will terminate the loop. Okay, so this is basically the mechanism behind Gaussian reduction. And if we apply some numbers inside, like this is the two bad vector in the previous example, and this shows how to do Gaussian reduction to get the shortest basis. So we will calculate the norm of v1 and v2. So there are these two numbers. So this is why I swapped vector c and vector d before, because this is actually longer. So I can perform a swap here. Okay, so the v1 is longer than v2, so we will do a swap. Okay, do a swap here. So the two vectors are swapped in the position. And then we will calculate the m. The m is actually the dot product of v1 and v2, which is these two numbers multiplied by each other and plus these two numbers multiplied by each other. And then divided by the norm of v1 and squared it. So it's actually this one. And then divide them, we'll get 1.01, something approximate to this value. And if we round off this to the nearest integer, we will get 1. So v2 would become v2 minus v1, and that it will become this one. So this is the first loop. Okay, so we do the second loop. The second loop is we calculate the norm of the two vectors, and then we see that, oh, the second vector is shorter. So we do a swap here, and after swapping, we'll calculate the m. Oh, so the m is approximately 99. So we will replace v2 by v2 minus 99 v1. So it will become this one. And then we have this one, and we do this process the last time, which is calculate the norm of these two vectors. So the second one is shorter, so we swap the position. And after swapping, calculate the m, which is approximately 2. And then we replace v2 by v2 minus 2 times v1. And then we'll get this. So we know that the basis vector would be 2, 0, and another is -1, 2. Oh, but it's a bit different. So what we talked previously is something like this, 2, 0, and 1, 2. But here we have this 2, and another is -1, 2. So actually, if we take absolute value, so the negative one will still become the positive one. So they are actually the same. Okay, so it doesn't matter because it's already the shortest. So no matter it's like this, -1, -1. Sorry. This one should be this one. This is -1, 2, and -1, -2, and 1, -2. Actually, these two, these four, after the Gaussian reduction are represent the same vector. Okay, so it does not affect the solution of the shortest basis problem. Okay, so we have these two shortest basis vector, and the first one would be the shortest non-zero vector within the lattice. Okay, so this shows how the Gaussian reduction is going to solve the shortest vector problem for us. Okay, so we will have some warm-up exercise. Okay, for example, if I love listening to J-pop music, and then YouTube Music is regularly reporting our total listening time. So if give us a minute, like in the past month or in the past year. So here I said that the time reported by the YouTube Music is the inner product or the dot product of the shortest basis vector of the lattice spanned by the bases, these two. So these two are slightly a larger number. So how to figure out the time? Okay, so actually, do you guys need some time, or maybe I give you uh maybe 2 minutes? So we will discuss it after 2 minutes. Okay, so it's actually a very wow. Okay, so it's actually a very simple math exercise. So we can do it by hand because these two numbers are actually quite small. So I can give you a very large number, so it will be more difficult to solve it by hand. So let me show you how to solve it by hand. So uh, for these two vectors, we compare the norm of these two vectors, and then we find that this one is actually shorter. Okay, so we swap the order, swap these two, and then calculate the m and do the replacement of vector 2, and we give us this vector as vector 2. And then this is actually shorter than the vector 1, so we do a swap again, and then we do the minus again, and then we further calculate the m. So here, the m here should be within negative 0.5 and 0.5, so it terminates the loop. And then this is the shortest vector behind. Okay, but solving by hand is not that efficient, so uh, we can use a program to help us. So this is a very simple Python function that help us to do the same logic in Python. So maybe you can demonstrate a little bit like this one. Okay. So we have these two vector C and D, which is the quite random numbers, and we can use this Gaussian reduction function, and then we plug in C and D as the V1, V2 here, and we get A and B. And actually, I use print within the function so I can see the steps of this program. So maybe we can perform. And then, so for this one, we can just use, so we do not use sage math here. So we just perform this one. Oh, sorry, we have sage here. Okay, so because I included the sage here, maybe I just do it in the sage shell. Okay. Okay, so it give me the step by step. So this is actually the steps in my slides. So these are the steps, and then this is the final answer. So this one is the final reduced V1, and this is the reduced V2. So this one is the shortest non-zero vector within the lattice, and these two are the shortest bases. So let me go back to the slides. Let's see, where's my slide? Let me see. Okay. My God. Just some small technical issue. Um, okay. So yeah, so this one, negative 914 and 0 would be the reduced V1 vector 1, and then the reduced V2 is 400 and 1012. So the first one would be the shortest vector. Okay, shortest vector. And then the combination of these two is the shortest basis, or we call it a good basis. Okay, but actually, so the Gaussian reduction can only be used in the two-dimensional space. So how to use similar algorithm to some higher dimensions. So we can use a LLL algorithm, which is named after these three guys. Okay, so it's actually a generalization of the Gaussian reduction in a higher dimension. So of course, we can use this LLL algorithm to replace the Gaussian function. It also gives the same result. Why it's this one? Okay. So if I just slightly modify the code here, and then I just comment out all this, the Gaussian process, and then I just use this one. Just use LLL. So actually this one will replace the whole thing because we don't need to manually write out the Gaussian reduction process. We just use the LLL, which is included in Sage. Okay, so we use Sage, so we will automatically get the algorithm. So we just use it by the matrix and then dot LLL, then you will actually give us the answer. So we just perform the program once again. sorry, this one. Okay, so it also gives us the reduced vector A and B, and then the answer to the previous problem is the dot product of A and B, which is this number. Okay, so it makes sense. Some big numbers in minutes. Okay. So we see the algorithm actually do the same thing as Gaussian reduction in the two-dimensional space. And actually, if it's a higher dimension, it will also work. So we use it in the next demonstrations. Okay. So for this one, okay, so this is actually a competition question in 2020. Okay, so let's check the function. So this function is would generate some keys. The keys include some numbers P, F, G, H, and then it returns these four numbers to the program. And then we have a ciphertext. So this is C. So C is the final ciphertext. So how is it generated? It's generated by encrypting the flag and by this P and H. So actually P and H is something that used to encrypt the original message flag. So P and H are actually called a public key. We can say it's a public key. It's some public information. Okay. Okay. And actually there's a decrypt program that I didn't put it in the slides. We can go to the parent directory, which is called NTRU. Okay. So in the source file, there's actually a decrypt function. Oh, I also didn't include it here. I included it in the GitHub repository. Okay, so there's a decrypt function given to you. So we don't have to construct the decrypt function. Okay, so we just figure out the other two parameters, because P and H are the public key, so it's given to you. And then C is the ciphertext, it's an encrypted flag, so it's also given to you. So we just need to figure out what F and G are. So if we have the combination of these 5 numbers, we can decrypt the flag. Okay, so how to find out F and G? So let's do some analysis. Okay, so we have P, which is a 2048-bit prime number, and F is a 1014-bit integer, and G is a 068-bit. It's also a prime. Okay, so these two are the private key, and this one is public. Okay, so we also have H. So H is calculated by, so let me explain a little bit about this function, gmpy2.invert. So actually the mechanism behind this one is, for example, if we put x and m inside, so it will return a y such that x times y would be equal to 1 modulo m. So for example, if we put in 3 and 11, we will get 4, because 3 times 4 equals 1 modulo 11. Okay, so we can just treat it as an inverse, the inverse of f. Okay, OP. So we can treat it as this mathematically. and then we'll times G mole P. Okay. So it's actually something like this. So actually we can use the equivalent relationship to define the H and the H's relationship with F and G and P. And then we can do a multiplication. So times both sides by F. You can get HF is equivalent to G mole P. And we can also observe the size of H because H is equivalent to something modulo P. So the size of H should be maximum 2028 because it's maximum the bit size of P. So it's maximum 2048 bits. So this is the maximum size of H. And then by this equivalent relationship, we can also write out a equation, which is HF minus G equals to K times P. And K is an integer. Okay, so we have this relationship. So how to figure out F and G? Okay. Also, H is also public. Yeah, H is also public. Okay, H is also public. So we have these two public information P and H, and we want to figure out the private information, which is F and G. So how to do this? This can be done by a very powerful formula called V times M. V dot M is called dot will be equal to vector W. So the previous two are matrix, and this one is a vector. So we need to put in something within inside. So for V, we'll put in some unknown. And for M, we'll put in some known stuff. And for W, we'll put in some target, what we want. So our target is the private key, right? So this is our target. This is our target. And we put in some unknown and known thing inside. So what we know, let me just move a little bit. Okay. What we know, P and H and sorry, put it wrong place. This is known and unknown. Known is P and H because public key are known. So P and H are what we know. And unknown should be F and G. And also this K is also unknown. This K is also unknown. So we have F, G, and K unknown. And our target is F and G. So how to put in this thing inside? We can see our target is F and G. So we must make some sacrifice. So we can put K here because K can help us, which is not inside here. And F and G, which one? Because G can actually be represented independently because after changing subject, G equals to HF plus KP. So we don't put G here because G can be represented independently. So we put F inside. So we put F and K inside this V and P and H inside this M, and the target will give us F and G. But the problem is still how to construct. So let me copy it to a next slide. Oh, what is this? That's interesting. How can I copy? Maybe I used the scroll function. Just scroll down. Okay, so we want to put in something inside V, M, and W. So W is very obvious, F and G. And M should be a transformation matrix. So it has 4 elements here. And then V is a matrix with 2 elements. So we just put F and K here and then figure out these 4 elements. Okay, so this is a matrix product and gives this. So by the mechanism of matrix, we have F times something and plus K times something equal to F. So it must be 0 and 1 here. So this will give us this result, F times 1 plus K times 0 give us F and no K here. And for the another, we have F times something and then plus K times another thing give us G. So we just recall what is G. G is actually this one. This one. G is actually HF plus KP. Okay, so H will be multiplying K. Okay, and then K, sorry. H will be multiplying F, and then K will be multiplying P. So this is P. So this is KF, KF. Oh, sorry, my bad. So F times H is this one, and then K times P is this one. But you may notice that it actually gives us F times H plus this K times P. Oh, but actually, I made a mistake here. Okay, this one should be negative. This one should be negative. This one is negative because after changing subject, this G goes here and we minus KP here. So we have negative here. Negative here. So if we have this matrix FK and HP, it gives us FH plus KP. So it's different from minus KP. So how to do some modification to V and M to give us the right one. So it's very easy. It's just make K becomes negative K. So it solves the problem because F times H, okay, this one, and then minus K times P will give us G. Okay, so that's how we come up with what's V and what's M and what's the vector W. So and then we have this transformation matrix here. So this is M, or we can call it the lattice. So this lattice contains 2 vectors. The base vector V1, or I use C and D. Okay, it would be 1H, and the other one is 0P. So this is a very long vector. Why? We can calculate the norm. Vector C will have a 1 plus K squared and then square root of it. And we know that H has a maximum of 2048 bits. So if it's 1 plus something which is of 2048 bit, so it will actually give us a number quite up near 2 to the power 2048. Okay, so it's a very, very long vector. And for vector D, the same. Vector D would be the norm, would be actually it's P. It's actually P. And then it's, so what's the size of P is also 2048. So vector D also have a length of 2 to the power 2048, which is approximate. So these are two very long vectors. How about FG? So this is the basis vector from the public key, because H and P are from the public key. So for the private key, F and G, how about this? So F and G, the norm is equal to F squared plus G squared. And then we can also find out what's the size of F and G is 1024 and 768 bits. This is 1024 bits, and this is 768 bits. So you see that this must be something like 2 to the power 1014 plus 2 to the power 0.068. So this must be far less than 2 to the power 2048. So after this reduction, so this is before, this is after reduction. We see that this is much, much shorter than the lattice basis before the reduction. So our target is to reduce this matrix. Okay, so we can have a program. Okay. So we have a program to reduce this. Okay, so what we get from the source is that is given to you. So we have the public key P and H, and then we have the encrypted flag or the ciphertext C. So this is what's in the output is H, P, and C. And then in the exploitation, we will just import these three numbers first. And then this is the decrypt function. It's also given to you. Okay, so we just need to find out F and G, and then also plug in P, H, and C. Then we will finish the decryption. So as we say, we just constructed a matrix, the lattice, which is 1H and 0P. So this is vector 1, this is vector 2. So we have these two here. And then, of course, we can perform the Gaussian reduction, but we don't. We don't need it because it can be achieved by a more simple LLL algorithm. So we just use this one. So this is the matrix combined by V1 and V2, this two one, and then perform the LLL reduction. So the first row of the lattice of the matrix after LLL reduction is actually the shortest vector. So we just perform the LLL reduction and then get the first row, because the index 0 means the first. So it gets the first row is the shortest vector. And then we just perform it. And then perform this, we get F and G. Okay, so this is the shortest vector, the two numbers of the shortest vector. And then maybe I can just print out what F and G are. Oh, then maybe I hide, comment out this too. So we can see how the exploitation is going to work. Exploit. Okay, so we output F to be this long string, and then G to be this long string. But they're actually a lot, it's already a lot shorter than H and P, because when you see the source, sorry, it should be the output. Yeah, you see the output, H is this long chunk and P is this long chunk. But after the reduction, it becomes this. So it's already a lot shorter than H and P. And then, so actually, this is already the shortest lattice. This is the reduced lattice. And then we just put in these two numbers. Just put in these two numbers. Because the decryption function, we just need to put in P, H, F, G, and C. And FG, we just find it out. Then we put in, and then we print the flag. But this flag will actually give us a number. Just give us a number. So we'll also call the long to byte function from the crypto package of Python. And then we will convert the number into the text that we want. So we just perform this. Okay, so the number would be this one. So this is what we get after putting in the fight parameters within the decrypt function. And then this is the decrypted number. And then we put in this number into the long to byte function, and then it will convert us back to the original message that I want to say. Okay, so this is the solution to the second demonstration. Okay. So I think the most difficult part is how to figure out the math problem behind. That is how to use this powerful formula and then come up with suitable parameters to form this lattice matrix. Okay. Okay. So let's go to the last one. The last one is a knapsack or backpack problem. Okay, so it's actually the algorithm that is used in this exercise is actually called the Merkle-Hellman knapsack crypto system. And it uses a public key derived from a super increasing sequence. So what is a super increasing sequence? Like this one, B1, B2 to Bn. So for each B, it will be greater than the sum of all the previous elements. For example, if I have 1 here and 2, so the third one must be greater than 3, so maybe it's 4 or 5, okay. And the next one would be maybe 50, and maybe the next one is greater than all the sum of all the previous, maybe it's 100, and maybe this is 500. Okay, so this is a super increasing sequence, okay, because each number is greater than the sum of all the previous numbers. And we get this super increasing sequence as B here, Okay, and then we also have a prime Q, which is less than the sum of the super increasing sequence. Sorry, I also made a typo here. This one should be greater. Yeah, this one is greater. Yeah, and let me see. Yeah, actually, I made two typos in this slide. This one should be P, should be B, because this is BRQ. Okay, so we have a Q, a prime number Q, which is greater than the sum of this super increasing sequence. And then we also have a private key, which is generated by this tuple BRQ. So the private key is BRQ. So B is the super increasing sequence. R is a integer, and Q is another prime. And these two numbers are co-prime, are very big numbers, maybe. This Q must be a very big number because it's greater than the sum of the super increasing sequence, but R is just an integer, but it's co-prime with this Q. So in general speaking, it must be maybe it's consecutive with R, or maybe it's also a very large number. So these three numbers are the private key. And then after generating the private key, we will generate the public key, which is another sequence. So this sequence is defined by this formula. Okay, but it takes modulo Q. So it will make the knapsack problem appear to be hard. And the encryption process is given in a message. And of course, the message is converted to binary, which is a combination of 1 and 0. And then something that we need to take note is that the encryption the process is performing from the right to left, because this line, it actually extracts the least significant bit first, and then it shifts right. So the left one is the least significant bit, and the next one is the second least significant bit, and then it go on to the right. So if we want to recover the message at the end, we need to do a reverse to reverse back, to do some reverse. So we do reverse to get the most significant bit first, and then we go all the way to the less significant bit. Okay, so we need to do a reverse at the end. Okay. And the decryption is actually use the ciphertext and private key and public key, private key to do the decryption. And the security assumes the ciphertext is a sum of all the message, because the message M just mentioned here, the message, for example, is for example, the message, if the message is 11001, so the vector M would be 11001. Okay. And then so M1 is this one. Sorry, this should be M0 is this one. This is M1 is this one, and then go on so forth. And then actually the encryption algorithm here ensures that the ciphertext is the sum of all the m times a, and m is each bit in the message vector, and a is the private key vector. So a is the private key vector, and m is the message vector. And the ciphertext is for each in each place in the message vector and the private key vector, we times each other, and then we get a sum. So if we don't know the private key, it's actually quite different to do the decryption. However, we can apply the LLL reduction to help us to find the shortest vector that can reveal M. So how to do that? We will construct a lattice A, a lattice matrix A. It has n rows, n columns for this, and then it actually has n plus 1 rows if we include this final row, and then it also have n plus 1 columns if we include the last column. Okay, so what's the elements within the first n rows? For the first row, it's 2 and all 0, and the last one is the first public key. And then for the second row, the second column is 2, and others remain the same. And this is the public key 1. And then all the way to the last one. The last one, this should be the n public key. This is the public key. If in terms of index, it's n minus 1. And what is n? N is actually the size of the private key. Okay, so how many elements are included in the private key? Sorry, it's about the public key. So this one, this public key. So maybe we can look at what we have on hand. This one. So this source will give us public key and encrypted flag. And for the private key, it's just the tuple BRQ. This is the private key. And public key, you actually have a lot. Let's look at the output. Public key will have, this is the first one, the second one, the third one, and all the way down. You actually have 200 something public keys. Okay, so we let the total number of public key be n, and this is the first public key, second public key, and the last one is the n minus 1 public key, because we start from 0, so the last one is n minus 1. So total we have n rows, and for the last row we have all 1 here, and the last element is the ciphertext. It's also a number. It's actually the encrypted key. This is the encrypted flag, or we call it the ciphertext. Okay. Okay, so we have this matrix, and we can, of course, we can perform algorithm to this matrix, but what's next? Okay, so this also includes some math behind. Maybe we can just perform the LLL first, which is, let me close off. So we just import the public key. I call it PK here. So all these public key are imported here. And then the ciphertext, the encrypted flag is here. And then n is the length of the public key, which is, I think it's about, maybe we can print it out to see. from C. Okay, so this should be N. Okay, so we have 278 public keys. So N is this one. So comment out N equals 2728. Okay, for the next one. So we can perform. So we just construct this matrix A, and then I think we don't print A because A it should be a very, very long chunk. And then we perform the LLL algorithm to A, and then maybe we can print the R to let you see. Okay, so just comment out the later one. So we construct the lattice A here, and then we reduce it by LLL. So let's see what's the reduced vectors. So it takes some time to run because it's 200 something dimensions. So we'll get something like this. So this is the reduced matrix. So it's a lot of things. Okay. So as you can see, in front there's something like -4, -2, and all zeros. And as we scroll down, it's still similar patterns, but the number of zero may decrease. And further scroll down, further scroll down, further scroll down. Okay. So it's something like this. So as you can observe, except the last two rows of the vector, we see that we just take a look at the last element, except this two, the most below two vectors. We just look at this one, 0, 0, 0, and we can look at more examples, 0, 0, 0. 0, 0, 0. Okay, 0, 0. Or I think most of them are with the last element 0. So this gives us some hints. Okay, so how can we achieve this? Okay, so we have this matrix. For simplicity, I don't use the index in Python because in computer, we use index 0 to present the first one and index n-1 or -1 to present the last one. But I use 1 to n for simplicity. Yeah. So we have this matrix A, and then we will perform some LLL reduction. So what's the reduced matrix would look like? For example, I just give them some name. For example, this is called row number 1. This is called row number 2, and ... This is row number n. So this row number n plus 1. So n here is 272, which is the size of public key. Okay, and then we perform some reduction. So maybe we do some reduction. And then there will be a row. Which is obtained from the sum of something. Because, for example, I use K1 times the first row, and then the K2 times second row, and I use K3 times the third row, and all the way to the last one, I use Kn times the row n, and then I use Kn plus 1 times row number n plus 1. So it's probably that one of the row after reduction is obtained or retrieved from doing this operation. Okay. So maybe we call this operation. So after this operation, the row be F. Okay. So maybe this row F is constructed by doing this operation. Okay, so what's the elements in this row or in this vector F? So this is one of the row. What's the elements inside? So the first element, it should be, because we use K1 times R1. Okay, so for the first column, we have K1 times this 2. Okay, because in the first column, we have 2 in the first row. So we use 2 times K1. And then okay, so for the second row, we have K2 times row 2, but the element in row 2 is 0. And for all these elements in other rows are 0. So we just plus 0 times K2 plus 0 times K3 plus dot 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 times plus 0 times Kn. And then we continue this process to the last one is 1 times Kn plus 1. So this is the first element, in, or the first column element in this vector F. So actually, because these are all 0, so I just did them. And then this is 1, so I just use plus. So this is simple enough. Okay. Okay, so for the second column, the second element. So we have all this 0, so only K2 is significant. So we have 2 times K2 plus K n plus 1, because all these are 1. Okay, and then it's just similar. 2 times K3 plus K plus n plus 1, and dot dot dot. And to the nth one would be 2 times Kn n plus Kn plus 1. Okay, and the last one, the last row. So this corresponds to this column. This corresponds to this column. The nth corresponds to this column. And then the last one. So we have K1 times public key 1. Okay, and then we have K2 times public key 2 plus, and then we just, the last one is Kn times public key n, and plus Kn plus 1 times the ciphertext. So we can use a summation sign to conclude these things. So this is maybe I equals 1 to n, and then Ki times public key I. Okay, so we can use this to replace this. So let's just erase this one plus this one. Okay, so this vector F is actually one of the row after the error reduction. And as we see from the previous shell output, we see that most of the last element is 0. So let's investigate what's going on. So if we want to make this as 0, this to be 0. So how can we make this to be 0? And also note that behind the encryption algorithm, we have this one. Okay. The ciphertext is actually the sum of the message vector mi times the private key ai. Okay. So sorry, this is not private key, this is public key. just take a closer look because A is in the public key. So this is the public key. So actually this is what we are defining PK in our exploitation. And this M is the message. This is the message vector. Okay. So ciphertext is the sum of MI times the PKI. So we can see that CT is actually the sum, right? 1 to n, and then MI times public key I. And actually, you may wonder what's MI. I can tell you. The message vector is something like 1 1 0 1 0 1 1 0 0, and dot dot dot, and the last 4 bits is 1 1 0 1. So this is the message vector. So we will have this message vector here, and then the ciphertext is obtained from using the first element in the message vector times the first element in the public key, and then plus the second element in the message vector times the second element in the public key, and then so on and so forth to the end, which is the size of the public key is 272. So we do this summation to obtain the ciphertext. So if we want to make this 0, okay, so maybe I just write in another way. This equals this times this plus I equals 1 and then MI PKI. So you see these two patterns are very similar to each other, and then they just one plus another. Okay, so I missed one thing. The K n plus 1 here. Okay, this one. So these two looks very similar, and this one is just something that multiplied by this. So if we don't want this one, that's very easy. Just make it 1. Okay, so maybe we make this be 1, this be 1, and then so this is, if this is 1, this is 1. It just solve one of the problem because we are just checking the relationship between Ki and Mi. So if we also define Ki be negative Mi, then the whole thing will be 0 because it just cancel each other. Negative Mi times Pki and plus Mi times Pki. So these two things will cancel each other. So we just take Ki be negative Mi, and then Kn plus 1 equals 1. So this will make the last element be 0. Okay. Okay, and then after taking this value, we can write out the vector f, which is one of the row after error reduction. So it is 2 negative mi plus 1, or we can reverse the order, but that is 1 minus 2 mi. Okay. So this is the first element, m1. And the second one is 1 minus 2 m2. dot 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 1 minus 2mn, and the last one is 0. Okay. Or we can just say the ith element in F is 1 minus 2mi for 1 and between 1 and n, and the last one is 0. So maybe I don't have enough space. Let me add another page after. Okay. So if we have this one, and the nth element, the ith element is this, and we can put in some substitution, because we know that the message vector only contains 1 and 0, 1 and 0. So if we put in, if mi equals 0, then we will know that fi equals 1 minus 2 times 0. It will give us 1. And if mi equals 1, then the the ith element in F would be 1 minus 2 times 1 will give us -1. Okay, so we know the transformation here. So if we let me see. Okay, so we know this transformation. So we know that actually one of the row in the reduced vector would be a combination of 1, -1, and 0. So let's see. For example, in the error reduction, we get some matrix like these. We have like 2, -2, -4, and 4 and -6. So there's a lot of different elements inside. But for a row, but if we have a row that only have like 1, -1, -1, 1, -1, and the last one, and the last one is 0. So we know that the unique elements, the number of unique elements will be equal to 2. Okay, so we make use of this property to find out the row that we want. So this is done by this line. So we will check I means the ith row in the reduced vector. Okay, so for this means for each row in the reduced vector R. So we will, maybe I can also print this out to visualize. If I don't do this, just print this out. So if I do this thing for each row in the reduced vector, we print the unique elements, because the meaning of this is the row, and this is from the first to the second last, because this means to the second last, that is not include the really last one. So the set function means the number of unique elements. So the length of the number of unique elements in the row except the last one, if it's, so let's see what's the number we have. Okay, sorry. Okay. So for each row, for example, in this last row, we have 6 unique elements in the first first n elements except the last. Okay, and then for this, we have seven unique elements, and maybe we just scroll up. We have maybe this row we have 5 unique elements, and maybe for this row, okay, we have 6 unique elements. But for our target row, uh, what's wrong here? Okay, for our target row, we will have 2 unique elements. Okay, so maybe we just find out what this row is. So if the length of the unique elements is equal to 2, then we will output this as f. So we will define this as f, and then we print this f out. So let's see. Perform that again. Sorry. So we will get this row. So that's what we want. So it only contains -1 and 1. So we finally find out the row that we want. That is only contains -1 and 1 in the first 272 columns, and the last one is 0. Okay, so this row contains the message that we want. Okay, so we have this row, and then let's see. So we finally find this row. So we now get the f. So this vector f is actually maybe we can write down a field -1, 1, -1, -1, something, and then the last is 1, -1, -1, 1, and 0. Okay, so I just write it down here. So this is what we get after the reduction. And then we do the conversion, because if we have original message is 0, then you have 1 here. If the original message is 1, we have -1. So we just do a conversion. The conversion or transformation. Is that if we have 1, then we'll make it 0. And if we have 0 and -1, we'll make it 1. And of course, the 0, we just leave it there, because as we mentioned previously, where is it? I will the LSB one, where is that? This one. Yeah, we will do a reverse at the end. We'll do a reverse. So the last 0 is actually, it doesn't matter, because when we do a reverse, you just go to the front, and it doesn't affect the value of the binary we get. So 0 is just 0. And we can perform this transformation. So we will get the new f, or it's actually the flag. Okay, so the flag vector would be like 0, 1, -1, -1, 1. Sorry. My bad. It should be 1 becomes 0, and -1 becomes 1. So this one will become 1, and this one will become 0, and this one will become 1, okay, and so on and so forth. And then the last 3 I performed with 1, 1, 0, and 0. Okay, so this is the last 3. The last 3 becomes this. And then, yeah, these correspond to this corresponds to this, and then the last is correspond to this one. Okay, and then let me see. Yeah, and then, but this is reversed. Okay, so this is reversed. We need to convert it back. So we would further do a reverse to obtain our flag. So the last one will go to here. Okay, the last one go to here, and then we'll have 0, 1, 1, and dot dot dot. The last one is 1, 0, 1. Okay, so all the things we just reverse it. So we go back from this direction, and go in this direction. Okay, so we use Python to help us with this. Okay, so in the exploitation, okay, we just first do the conversion. So after the conversion, do the conversion. Okay, and then do this one. Okay, so this actually does the conversion and also do the reverse. Okay, so we can print the binary of the flag now. Did I save it? I think I didn't save. Yeah. Okay, so this is the binary flag. Okay. Why is it? Did I save the program? Why it doesn't work? Let me save it. Okay, so it gives us the binary. Okay, so this logic would do the conversion. If original is -0, we'll give 1 and else give 0. And then we'll this one is actually doing the reverse. Yeah, this one is doing the reverse, and then will give us the flag in binary. And with the flag in binary, we can just do the you use this int function to convert it back to decimal. Okay, so maybe I'll print all of them out. Okay, and then finally, we use long to byte to convert this decimal back to some text. So let me save it and then run it again. Okay, so it gives us the flag here. Okay, so this is actually the last demonstration. So I would say this topic, the math behind is the most challenging. And you see the program is actually not, the coding of the program is not very long, not very complicated, but you need to figure out why to set up the logics behind. Okay. So yeah, so this actually describes summarize the process. Okay, so maybe let me end my presentation here, and these are the references I used, including some sharing on the competition questions, some write-up on the competition questions. Okay. Okay, so maybe you guys can ask some questions if you have any. Thank you.